So let's come back to this small signal voltage gain of our common gate amplifier. So I've copied our basic circuit here. This is the same thing we saw in the previous video. And here's the small signal equivalent circuit that we had for the circuit above in the previous video as well. And so the main thing that I want to change here is previously we had said our R0 was equal to infinity, but now let's change that and say we have some finite value of small signal output resistance. And so of course in our small signal circuit, that means we're going to connect R0 between our source and our drain. So now we have some small signal output resistance R0 as shown here. So let's define a couple things which are going to make it a little bit easier for us to analyze this circuit. So I'm going to do these in blue so they stand out a little bit. So as we saw before, we're going to have some current going through this small signal resistor R0, and so that's going to be dependent on the drain to source voltage, which is of course between these 2 points here. So let's define our VDS, and what we're going to do is we're going to utilize KCL at our drain and our source. So we're going to have some current coming into here, and so let's go ahead and for simplicity just call that I1. It's going to be splitting into 2 parts, and so let's go ahead and call this IX. So we're going to have an IX in R0, we're going to have GM-VGS, and then at our source they're combining again such that we have the full I1 value going through that RSI. Okay, so our basic idea as always, if we're looking for a small signal voltage gain, is we're looking at the output side of the circuit, we're looking at the input side of the circuit, and we're trying to relate VI to V out. So of course ultimately we're looking for small signal voltage gain, which is V out divided by VI. So as we normally do, let's start by looking at the output side of the circuit. So what I'm going to do is I'm going to combine these 2 resistors in parallel, and we can see we're going to have I1 going through those resistors, and it's going to be flowing upward such that we create a voltage drop like this. Now as we've often seen before, that polarity is opposite of this output voltage polarity, so we're going to need a negative sign in our equation. So we can come down here and we can write that our V out is equal to negative I1 times the RD in parallel with our load resistor RL. And so we can, let's call this equation 1, and we can actually modify this or improve this a little bit if we adjust or we get a more detailed equation for that I1 rather. So from KCL, what we can say is that our I1 is going to be equal to the sum of those 2 currents. So we're going to have GM times VGS, and then we're going to be adding to that IX, but I'm going to go ahead and substitute in and say we know IX is going to be VDS over R0. Well, now we can improve that a little bit more by doing KVL. So let's come in here and let's say we want to use KVL to define that VDS value. And so we can do that by looking at this KVL loop here. So we can say our VDS is going to be equal to V out plus VGS. Okay, so let's come down here and let's update this a little bit. So we can say this is GM VGS plus, and let's pull out that 1 over R0, and then we have V out plus VGS for our VDS. Okay, and so we can actually rearrange that a little bit, and so we can say I1 is equal to, let's get all of our VGS terms together, so we have VGS times GM plus 1 over R0 plus V out divided by R0. And so let's call that equation 2. Okay, so now let's go to our input side for sort of our last unique piece of information. So if we do a KVL on our input side, we can relate our VGS and our VI. So we see it's going to include, as well as those 2 voltages, our voltage drop across this RSI resistor. And so because I1 is going from right to left, we're going to have a positive voltage drop from right to left as well. So if we write it in terms of VGS, we can say VGS is equal to negative VI minus that voltage across RSI. And again, we see we have that full current I1 flowing through that resistor. So from KVL and Ohm's law on our input side, what we're going to see is we have our VGS is equal to negative VI minus RSI times I1. And so let's call this equation 3. Okay, so at this point we have all of the information, all of the unique information that we can get from this circuit, and now it's just a matter of sort of playing around with these equations, combining them, substituting, simplifying, to get our overall expression that we're looking for, which is this V out over V in. So let's start by substituting equation 3 into equation 2. So we're going to take this expression for VGS, and we're going to plug that into our equation 2 here. So let's say we want to substitute equation 3 into equation 2. And I'm not going to go through all of the algebra of that, but if you do have questions about that, definitely let me know. But when we do that, we get a more complete expression for our I1 in terms of our VI as opposed to the VG. And so again, notice that when we do this, we're going to get an I1 over here on this side of the equation. So we're going to have to sort of move that around and get our I1s together. But our final result for the I1 is going to be negative VI times the quantity GM plus 1 over R naught plus V naught over R naught. All of that is going to be divided by 1 plus RSI times GM plus 1 over R naught. And so let's call this equation 4. Okay, so now what we're going to do is we want to substitute this equation for I1 back into our initial equation, equation 1, for our output side. So substitute equation 4 into equation 1, and so we're taking this expression here for our I1, and we're going to plug that all the way back up in here in our expression 1. And so what we can note is that we have a negative sign in each of these expressions, so that's going to cancel out, and that's going to leave us with a positive sign. So let me go ahead and write sort of that first, what the equation looks like after we first substitute before skipping over some algebra to get to our end result. So if we plug that in, again, we're going to have a positive RD in parallel with RL out front, and then all of that is going to be multiplied by our IL expression, which is, or sorry, not IL, I1, which is going to be VI times GM plus our 1 over R naught minus our V naught over R naught. So notice we had to change the sign there as well. And we have that is going to be divided by 1 plus RSI times our GM plus 1 over R naught. And so the reason I had to change that sign there is again, in this equation, we didn't necessarily have the negative sign out front of everything, but rather I factored out a negative so that this became positive and this became negative, and then we had sort of the negative sign out front of everything. Again, if you have any questions about that, definitely let me know. So what we can see here is now we have only V out, we have V in, and everything else is either a transistor parameter, GM, R naught, or some resistor in the circuit, RD, RL, RSI. So from here, it's just a matter of algebra, getting all of the things in the right place, and then once we get that, we can simplify a little bit, and if we do that, we'll get a voltage gain expression of AV, which again is equal to V out over VI, and we'll end up with, in the numerator, we'll have our RD in parallel with RL still, and that's going to be multiplied by that GM plus 1 over R naught. And in the denominator, we're going to have 1 plus RSI times GM plus 1 over R naught plus, and now we have RD parallel RL divided by R naught. And so this would be our more detailed voltage gain expression compared to what's shown in the textbook, because we've considered a finite small signal output resistance. However, we could easily jump to that expression. So let's say instead, now we want to go to a more ideal case, and we want to say our R naught is equal to infinity. Well, we can adjust this equation, and we note that this term is going to go to 0, this term is going to go to 0, and this term is going to go to 0. So all of those would be divided by infinity. And so what we see is if we have an infinite R naught, then our voltage gain equation is simply going to become, we're going to have our GM times RD in parallel with RL in the numerator, and in the denominator, we're going to have 1 plus GM times RSI. And so this is actually the equation that you'll see on page 235 in the textbook.